Okay, we're going to talk about linear regression now. This is the last subject we're going to go over from the book for this class. It is a useful skill. Basically, what we're doing is trying to come up with a line that a linear line that matches a data set. Usually, what we use for this is the least squares regression line. So it's the line which gives the smallest variation on average for the data. It's also called the line of best fit. So we've got y hat here, which is our projected y value, is you know an intercept plus a slope times the recorded x value. So remember in our data set we've got 2 points in our data. So if you think back to the last section, we've got the quarterback ratings and the number of touchdowns they threw during the season. So this would be touchdowns thrown during the season, and this could be projected rating. We'd have an actual recorded rating as well. So the slope in this case is given by this formula here. Again, just like with the correlation coefficient ones, you need to pay attention to where these squareds are in relation to the summation and any parentheses. So this is the sum of the x squared values. So I'm trying to remember some of those data values offhand. The first one on the list was 46 touchdowns, so this would be 46 squared plus, I think the next one was 18 touchdowns, 46 squared plus 18 squared plus 12 squared plus whatever they are. And then this is that sum, 46 plus 18 plus 12, and then you square that sum. So you do need to be careful to pay attention to those, where the parentheses are and where the exponents are. Right, n again is the number of data pairs we have. We've got the explanatory value variable and the response variable. So this would be touchdown scored and quarterback rating, touchdown scored, quarterback rating, number of quarterbacks we were looking at. The intercept then is given by this equation. So we've got the sum of the response variables over n minus that b1 value that we just calculated, the slope, times that sum of the x variables over n. So that is how to find an equation for the possible line. And really it's going to be the equation that minimizes. So we've got these y values, and for each x value we've got data for, we're also going to have a projected y value that will be y hat sub I. And these equations are going to give the equation for a line that gives the smallest average difference between projected y and measured y. So like we talked about in the last section, we can see if the correlation coefficient is statistically significant, and if we can use a linear regression to project it. If it is, we still need to look at the scatter plot and see if it's a linear relationship. If it's not statistically significant, the results are not going to be meaningful. If you do a linear regression, it's going to be meaningless because, yeah, it's going to give you an equation, but it's not going to tell you anything because the R value is not significant. I could use these equations to plot to come up with an equation for something that looked like a random circular scatter pattern. It would give me a value. it wouldn't mean anything. So let's look at an example of finding a least squares regression line using the calculator, because as we did see in the last section, this is built into the TI-8384. It's also very handily built into Excel. You can do it right from the graph. You can, if you add a linear trend line and tell it to show you the equation, this is what it does. So if we're looking at, the school board is looking at the relationship between class size and performance on state tests. So it's collected data from various schools around the district, and we're looking at 8 classes. Each pair represents class size and corresponding average score on the achievement test. So we've got our 8 classes, there's class size, and the class's average test score. So we're looking to see if there's a significant linear relationship between the test score and the class size at the 0.05 level of significance. I'm thinking that class size is going to be the variable that's affecting things, and class and test score is the response variable. If the relationship is significant, we want to find the least squares regression line for that relationship. So, is there a possibility that test score would influence class size? No, class size really comes first if you think about it in terms of time. So we're looking at class size affecting test score. Yes, that's possible. There's a lot of talk about how lower class size is better learning and so on. So class size would be an explanatory variable, and response variable would be y. So we can go in and we can enter the data, class size for list 1, test score for list 2, tell it we want to calculate a linear regression, hit enter, and there we go. We've got our slope and y-intercept in addition to the correlation coefficient. So if we look at this, we've got our correlation coefficient 0.977575. That is quite likely to be significant. It's very close to 1. Coefficient of determination is 0.955, so that would determine quite a bit of it. So if this turns out to be significant, then we've got our regression line right there. But our next step is really to determine whether or not that is significant. So we need to look at the critical value for a 0.05 level of significance. So we can go back to table I in appendix A, and we find that that critical value is 0.707. So the absolute value is 0.978. It is greater than 0.707, so there is enough evidence at the 0.05 level of significance to conclude that there is a correlation between the two variables that is statistically significant. Right, so we can look back here at our results and pull those out and put them into our equation. You'll note it tells you what equation you're fitting to, so you can see that that's ax plus b. The textbook and a lot of other things about regression call this b0 plus b1x. So b1 is clearly a, b0 is clearly b. So there's our a value, negative 1.043, and our intercept was 103.085. There's our equation. If we plot this, there's our scatter plot of the data, and there's that line we just calculated. And that seems like a pretty reasonable fit. Yeah. So we should not use a regression if we graph this and it's clearly nonlinear. We should not use a linear regression if the correlation coefficient is not significant. We should not use a linear regression if we want to make a prediction about a value outside the range of the sample data. So if, for example, we wanted to know what happened with the class size of 40, that's well outside of our data. We can't do that with what we have. We can't use this regression if the population is different from that with the sample data were drawn. So if this is all data from grades 1 through 3, I could not use this correlation to predict a relationship for class size and test score for high schoolers, for example. It's a different underlying population. So let's use this. We could use this equation to predict approximate test score for these following class sizes: 16, 19, 25, and 45. You go ahead and do that and take a minute and unpause when you're ready to move on. Okay, so basically we can just put 16 in there. We can project that the class is likely to get about an 86% on it for a class size of 16, 83% for a class size of 19, 77% for a class size of 25, and we don't want to even go there for a class size of 45 because it's outside of the sample range, and we can't responsibly make a prediction for something outside of the sample range. Ooh, excuse me. All right, so we have a list of selling prices for used Land Rovers and their ages in years. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 Land Rovers. 3 years old sold for that much, 1 year old sold for that much, etc. We want to find a linear regression model for predicting the price of a used Land Rover based on its age with a 0.05 level of significance. All right, so our explanatory variable and response variable, we want to use the age. We've been upfront about that to predict the selling price. So age is the explanatory variable, selling price needs to be the response variable. All right, we can set this up in the calculator. Put age in L1, price in L2. Tell it we're calculating a linear regression. Hit enter, and there is our correlation coefficient, right? So the next step before we do anything with the slope and intercept is to see if this is statistically significant at the 0.05 significance level. That's one thing we need to do. The other thing we need to do is check to see if the scatter plot shows possible linear relationship. So we can do that. We get this. And yeah, maybe. I'm kind of thinking it looks more parabolic almost. But yeah, it's possible linear relationship. Possibly not. It's kind of on the and a lot of statistics is and especially data analysis is it could fit that. Let's see sometimes. So yeah, I could put a straight line in that makes sense. It maybe a little bit above those, probably right through those. Probably going to be closer to that, so about like so. Yeah, a straight line through that. Straight line through that would make sense. Right, so let's look at the critical value for the 0.05 level of significance. Again, this is on table I in Appendix 8A. So for our 10 cars, and the 0.05 significance level, our critical value is 0.632. So we've got a 0.863 for an absolute value. It's greater than 0.632, so there is a possibility of a statistically good evidence for a possible linear relationship between these two. Okay, so now I can go back and look at my results. There is my slope, and there is my intercept. I can put those in. There's my intercept. There's my slope. This is my regression line. So I can use this. What's my range here? I've got 1 through 4 years for my range in ages. So, selling price of a Land Rover that's 2.5 years old. Yes, that's in the range. I can do this. I'm just going to put 2.5 in there. Selling price for a Land Rover that's outside of the range of my data. I cannot make that prediction. Selling price of a Land Rover that's 3 years old. I get 1 through 4 years again. I can do that. I put 3 right in there for X, and away I go. There we go. We get $23,407 for a 10-year-old one. It's not appropriate. Oh, and I did not read closely enough. Since this is for Land Rover Freelanders, and that was using it to predict Land Rover Range Rovers. I completely missed that. This is a different underlying population. We didn't do anything with Range Rovers. We did Land Rover Freelanders. This is the first time I've seen them try to slip in a trick question quite like this. Range Rover and Land Rover are very similar, and I caught onto Rovers and did not catch the difference. So please be a little careful about that. So yeah, this would not be appropriate because it's a different underlying population. All right, so let's look at a linear regression model, start to finish here. We've got average monthly temperatures and corresponding precipitation for 1 year in Key West, Florida. Okay, there's our data. We want to create a scatter plot. Does there appear to be a linear relationship between X and Y? What's the correlation coefficient? Verify that it's statistically significant at the 0.05 level of significance. Find the equation of the line best fit, or best fit line. Really should be best fit line. It's just more convenient to say. Find the coefficient of determination. If it's appropriate, predict the monthly precipitation totals for a month in which the average temperature is 80 degrees. If appropriate, predict the monthly precipitation in Destin, Florida for a month in which the average temperature is 83 degrees. I'm going to start with these for a moment, just while I've got the table somewhat handy. Okay, this is for Key West, Florida. That is our location. And our range is 75 to 90. So I'm just going to start with checking appropriateness. 80 is in that range, Key West. Destin is a different location. I'm not sure where in Florida that is. I'd have to get a map and search. But it is not Key West at any rate. So it is a different underlying population, so it's not appropriate. Okay, so we need to start with first what is going to be our X variable and what is going to be our Y variable. It's not clear which influences another. We could choose either. In this case, based on the questions the other questions you're answering, let's go ahead and use temperature for X because they're asking you to predict precipitation given a temperature, and that's the form of the equation that's going to be useful. Using temperature for X is going to give us an equation that's useful for the predictions they're asking us to do. So here is our regression model, our scatter plot, and yes, it looks like we could have a possible positive linear correlation there. We could also have a possible logarithmic correlation, but linear is certainly possible. Hello, kitty. There we go. There you go. All right, so we can move on. If we put these in the calculator, as we've been doing throughout, we have our correlation coefficient of 0.859. We've also got our coefficient of determination right there is 0.738. Right, so we can look at table I in Appendix A and see that the critical value at the 0.05 level of significance is 0.576. Now again, we'll need to know the number of samples, number of data pairs for that. But our 0.859 is greater than that 0.576, so yes, it's statistically significant. Right, how many points did we have? Yes. 1, 2, 3, 4, 5, 6, we had 12 data points, 12 data pairs. There we go. There's our slope and intercept, right? So we can go ahead and use those. We've shown that the likelihood is significant. There's our coefficient of determination. So approximately 73.8% of the variation can be attributed to the relationship between temperature and precipitation. Oh, right, there we go. Sorry, I skipped ahead too far. So we can put that slope and, sorry, there's the slope and intercept into our equation here. We can use it to make predictions, right? 80 is within that range of x values, so we can do this. We can put 80 in right there, and we get approximately 2.58. Should approximately, we can reasonably estimate 2.58 inches for precipitation for a month with the average temperature is 80 degrees. And then, as we mentioned in the beginning, the data was collected for Key West, not Destin, so it's not appropriate to make regression estimates. All right.